Can the same AI that generates software also design commercial digital hardware? Millions of developers now use AI to generate software every day. But does the same approach work for commercial RTL design? The answer may surprise you. If AI can generate software, shouldn't it generate commercial RTL the same way? After all, both are written as code. This assumption sounds reasonable, but it overlooks how commercial hardware is actually developed. The answer is no. Commercial RTL development follows a completely different engineering workflow. Let's compare 7 key differences between AI for software development and AI for commercial RTL design. Difference 1. AI deliverables. Software AI typically generates source code, unit tests, and documentation. Commercial RTL development requires much more. Besides RTL, engineers also need self-checking verification, logic synthesis, QOR analysis, and professional engineering documentation. Commercial hardware requires a complete engineering project, not just generated code. Difference 2. Prompt engineering. Software AI often starts with a functional description. Commercial RTL development starts with a complete engineering specification. AI needs engineering context, interface details, clocks and resets, target FPGA or ASIC technology, verification requirements, and expected deliverables. Better engineering specifications enable AI to generate better commercial RTL. Difference 3. Success criteria. For software, success usually means the code compiles, the tests pass, and the application works correctly. Commercial RTL has a much higher standard. The RTL must be functionally correct, meet timing requirements, optimize area and power, and achieve good quality of results, or QOR. Commercial RTL is judged by engineering metrics, not just functionality. Difference 4. Technology awareness. Software AI is usually independent of the target hardware. Commercial RTL is not. I must understand whether the design targets an FPGA or an ASIC and generate technology-aware RTL that maps efficiently to the available hardware resources. Understanding the target technology leads to better hardware implementations. Difference 5. Validation. Software AI is commonly validated by compiling the code, running tests, and debugging errors. Commercial RTL follows a much more comprehensive engineering flow. Engineers perform RTL review, functional simulation, lint checking, logic synthesis, static timing analysis, CDC and RDC checks, followed by QOR analysis. Commercial RTL requires complete engineering validation before it can move forward. Difference 6. Hidden AI errors. AI-generated RTL may simulate perfectly and still fail as a commercial design. Timing may not close, area may become excessive, power consumption may increase, or the QOR may be unacceptable. Passing simulation alone does not guarantee commercial quality hardware. Difference 7. AI is only the beginning. In software development, code generation is often the primary objective. In commercial RTL development, generating RTL is only the first step. The design must still be verified, synthesized, analyzed, documented, reviewed, and optimized. Commercial hardware development begins after the RTL has been generated. So where is the real problem? Most AI tutorials stop after generating RTL. Commercial semiconductor companies do not. In industry, generating RTL is only one milestone in a much larger engineering process. Delivering commercial quality hardware, not simply generating code, is the real challenge. To bridge this gap, commercial RTL development requires a structured AI engineering framework. Better engineering prompts lead to better AI output. Better engineering review leads to better design decisions. Better AI iterations lead to better RTL. A structured commercial workflow brings all of these together. A complete AI engineering workflow starts with engineering requirements and an RTL design specification. AI then generates the RTL, followed by RTL review, self-checking verification, waveform analysis, logic synthesis, QOR analysis, engineering documentation, and engineering review. This is how AI becomes an engineering assistant throughout the complete RTL development process. This is exactly what we teach in commercial RTL design. Using AI, learn what industry needs. Instead of focusing only on AI-generated RTL, this course shows how AI can be used throughout the complete commercial RTL engineering workflow, from engineering requirements to commercial quality hardware development. What makes this course different? It combines an AI-first engineering workflow with practical hands-on RTL development. You'll learn technology-aware RTL design for both FPGA and ASIC targets using anti-gravity IDE and the OSS CAD suite. Along the way, you'll generate commercial engineering documentation, analyze QOR, and follow a complete RTL to QOR engineering workflow inspired by modern semiconductor industry practices. Who should take this course? Whether you're an engineering student preparing for your first semiconductor job, a fresh graduate entering the VLSI industry, an FPGA or ASIC engineer looking to improve your AI-assisted workflow, a working professional upgrading your skills, or a faculty member teaching digital design or VLSI, this course is designed to help you develop practical commercial RTL design skills using AI. AI is changing the way engineers develop digital hardware, but generating RTL is only the beginning. Commercial hardware is built through engineering verification, synthesis, QOR analysis, documentation, and continuous review. Don't just learn how to generate RTL with AI. Learn how industry uses AI to develop commercial quality digital hardware. If you're ready to learn AI-assisted commercial RTL development, we invite you to join us in commercial RTL design using AI. Learn what industry needs. Learn practical engineering workflows, build commercial quality RTL projects, and develop the skills expected by today's semiconductor industry. We look forward to seeing you inside the course.